In this video, we will prove that if A belonging to K is algebraic of degree n, then degree of f of A over f is n. A is algebraic of degree n means A satisfies a polynomial of least degree n over f, and degree of f of A over f means dimension of f of A over f. So we have to assume A to be algebraic of degree n and establish the dimension of f of A over f to be n. So we'll consider A to be the given algebraic element of degree n. Then by the definition we have A satisfies a polynomial of degree n. Now this algebraic of degree n, so it must be minimal polynomial. So being minimal polynomial, by the proof that was given in the previous video, that p of x will be irreducible. So since p of A is 0, we have this implying a power n alpha 1, a power n minus 1 and so on plus alpha n to be 0, and from which a power n we get as negative of all this. We shall name this as 2. And this implies that a power n is a linear combination of 1a and so on a power n minus 1. Equation 1 is this. This is equation 2. So from here we conclude that a power n plus 1, when we consider we are multiplying both sides by a, so we get this. But again this involves a power n, that can be replaced by this. So whatever may be the power more than that n, you will have that to be linear combination of 1a and so on a power n minus 1. So proceeding like this, a power n plus k is a linear combination of 1a and so on a power n minus 1 for k greater than or equal to 1. Even a power n also you are getting. So k greater than or equal to 0 we can have, k greater than or equal to 0 also we have. Now let T be the linear combination of 1a square and so on a power n minus 1. That is, it is the collection of all elements of the form beta naught plus beta 1a and so on beta n minus 1 a power n minus 1 with betas from capital F. Now in first we claim that this T is a subfield of K. That means we have to prove that for x and y in T, x minus y belongs to T. Again for x and y in T, the product xy belongs to T, and every non-zero element of T has inverse in T. So first we notice that 0 belongs to T, therefore T is non-empty. And we shall take two elements x and y in this way. When you consider the difference, this is what you get. That is again a linear combination of 1a square and so on a power minus 1. Therefore, it's a member of T. Now, the second one, it follows from 3, means when you multiply two elements like this from T, the powers of A, it will be 1 a square and so on a power n plus 1 and so on it will be. So but again because of this statement we can have the product again to be linear combination of 1a square and so on a power n minus 1 only. So you will have the product to be again a member of T. Now we will have to prove that every non-zero element of T has inverse in T. So for that we shall consider U to be a non-zero member of T, and U again being a member of T should be of this form. You shall take h of x to be this, so that h of A will be just x replaced by A. You have this, but you have assumed U to be non-zero, so your h of A is non-zero. If h of A is non-zero, P of x cannot divide h of x, because P of A is 0 and that is the minimal polynomial. So minimal polynomial satisfied by A will divide any polynomial which A satisfies. But here A doesn't satisfy it, so P of x cannot divide h of x. So also since P of x is irreducible and p of x does not divide h of x and p of x must be relatively prime. So this implies that there exists, your p of x is irreducible. It's something like this. See, I have a number, say 3, and my 3 does not divide 5. So when I consider the GCD of 5 and 3, it has to be 1. Right? If suppose I have 3 dividing that number means 6, then you cannot have GCD to be 1. So 3 is, p of x is irreducible and p of x does not divide h of x. So you have this. So that means we can find 2 more polynomials. So all this you have studied in Euclidean, in Euclidean domain, of course, but fx is Euclidean domain. Euclidean ring or domain, you can call it as. So you have h of x into t of x plus p of x into r of x to be 1. This 1 is nothing but constant polynomial. So from here you have h of a into t of a plus p of a into r of a to be 1. You are evaluating this at a, so you get this. And you have your p of a to be 0, so you are left with only this. And but your h of a is u, so you have u into t of a to be 1. And because of commutativity in t, you have t of a into u also to be 1. So that tells that t of a is the inverse of u. So t of a, again it's a member of capital T, because whatever may be the index of a, because of the third equation, this we will have that to be t of a to be a member of T. So that proves the third part of this first claim. Next we claim that this T is nothing but f of a. This T is nothing but f of a. So for that we have to show that a T contained in f of a and f of a contained in T. Now T is a subfield of K containing f and a. T is a subfield, that's now we proved, of K. It contains both f and a. A is there. You can make the rest of them to be 0 and beta 1 1, so that a will be there. And if you have a, see, once you have this element a, you know pretty well that betas are present in f. So it is only the question of a whether it's present. Yes, it is obviously present. So it is the field of K, one of the subfields of K containing both f and a. But f of a is the smallest field which contains both f and a. So f of a must be contained in T. Name that as statement P. Also, as f and a are in f of a and f of a is a subfield, the elements alpha naught and so on should be in f of a. Because f of a is a field, subfield, so basically every subfield is a field, so these are all present. So T has the sum of all this. T is also a field, so you have T to be contained in f of a. So if you name this as Q, from P and Q, you have T to be f of a. Now we claim that degree of T over f to be n. That's in claim 3 that we have. That is, dimension of T over f is n. So that means we have to produce bases with n number of elements. Now because T is nothing but this, T is obviously spanned by the elements 1a and so on a power n minus 1. If you are able to prove that these elements are linearly independent, then that will form a basis. Number of elements being n, the theorem will follow. So we shall, to prove that these are all linearly independent, we have to consider the linear combination, equate it to 0. Now if all the scalars are non-zero, then A satisfies a polynomial of degree n minus 1, which is less than the degree of p of x, which is not true. Because p of x is the minimal polynomial of degree n satisfied by A. So if you are assuming this means, then A will satisfy a polynomial whose degree is less than that of the minimal polynomial. Hence alpha i's must be 0. So that in turn implies 1a and so on a power n minus 1 are linearly independent. And so this one form a basis of T, and hence dimension of T over f is n. So degree of t over f is n, but t is nothing but f of a. So degree of f of a over f is n. So we have that degree, whenever a is algebraic of degree n, degree of f of a over f is n. Now we'll make this remark. This was once asked in section A in the university. So do we have f of ab and f of ba to be the same? Both are the same because of this reason. If a belongs to k, then f contained in f of a contained in k, and if b belongs to this, you have this. Adjoining b to f of a, we get f of ab, which is denoted as f of ab, and it is the smallest subfield of k containing f, a and b. Similarly, adjoining a to f of b, we get f of ba, which is denoted as f of ba. This is f of b, adjoining a to it, you get this, which is denoted as this. And again, that is the smallest subfield of k containing f, a and b. As there cannot exist two smallest subfields containing f, a and b, we should have f of ab to be equal to f of ba. In the next video, we will prove that if a and b are algebraic, then the sum, the difference, product, the quotient are also algebraic over f. So that and then the algebraic extension, regarding the algebraic extension, we have a theorem. So both of them will be discussed in the next video. Thank you.